Okay, let's dive into your mineral story.
So, hi everyone. This is second episode on What on Earth, and we are your nerdy aunties, Veronica and
Pika!
who just can't shut up about the things we love. And boy, we love things.
Lots and lots of things. This is starting out to be amazing. Yes, let's do this.
Yeah.
Show me some
So,
hard things.
yeah, this is gonna be very hard episode for me. We have to have like a sound effect, meh, 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 every time I do some word pen.
Yeah, to talk to the listeners about some background, Veronica and I have been reading a lot of romantasy
Yes.
together. Yes, therefore, we use a lot of weird language here sometimes.
Yeah. Although we had this amazing idea about recording, bonus episodes when we discuss fantasy worlds in case of geology.
Mm.
And that would be great because it would force me to start reading Onyx Storm, which I've been lagging behind.
Ooh, we have to start that soon.
Yeah, we finished Iron Flame and now we are transitioning to Onyx Storm. No spoilers, but we will do separate episode about that. I think it deserves, especially that they are using, minerals and use some sort of pseudo metals and stuff. I was kind of digging into it. I was already
I'm very much ready for you to nerd out about that because I'm not a mineral expert. I leave that up to you. So bring it some other time.
We have to explain what are minerals and what is the difference between mineral and a rock. I know it's often confusing, and often I get photos of rocks and people are like, what is this mineral? And I was like, first of all, it's a rock.
You're one of those.
Yeah, see, I'm not this humble person in science communication. That's why you have science communication degree.
You are the know-it-all scientist. I'm the Hermione Granger of minerals. I like it.
Yes, or rocks, especially
rocks.
But let's dive in. The simplest answer is that minerals are made of atoms organized in structure, and rocks are made of minerals. Makes sense. Super simple. We can finish the episode. But to make it a bit more structured, there are certain criteria to classify something as a mineral, because not everything which is shiny and pretty is a mineral. It can also be ugly and not so shiny. So the first thing, it has to be naturally occurring substance formed by natural geological process.
So we've heard a lot of talk about these artificial diamonds, right?
Exactly. This is where I was going. Oh my God, I love this. So I was so for all those, girlies with lab-grown diamonds, I have very bad news for you. These are not minerals. These are actually...
Your boyfriend would propose with one of those, you would definitely say no.
I don't know. I just also don't like diamonds. Give me sapphire, much prettier. So the lab-grown diamonds are not diamonds. I mean, they are diamonds. They have the same structure, but they are not they are not nature formed. They are lab-grown. Actually, during my PhD, I was using instruments which could produce diamonds. So my PhD was in the realm of experimental petrology, where we were producing our artificial samples, our artificial rocks, very, very small, super small, like micrometer, so not even centimeter samples. And if people were working with high enough pressure and if in very specific conditions, they could get diamonds in their samples. That was not me, but I have friends who actually were growing tiny, tiny little diamonds during their PhD. Pretty cool. But again, not actually minerals. We call them phases.
According to the generally accepted definition.
Criteria. Right. Exactly. Yeah. So, yeah. It must be also a solid substance in its natural occurrence. So, for example, water is not a mineral. So, it has to fulfill all the criteria. And super easy. Barely an inconvenience. It also has to have well-defined crystallographic structure. So like obsidian, volcanic glass, the one where you fight White Walkers with. it's not a mineral. How
What?
this episode became like pop culture reference for fantasy, I don't know. I'm just going with it. Then you have opals, which are very pretty, but also not considered minerals, and they should be called mineraloids, if I pronounced it properly.
So what do you mean by this crystal? What did you say? Structure thing?
So it must have well-defined crystallographic structure. So minerals are like scaffolding. You have structure, and in the junctions, you have atoms. And those atoms create like lattice, and it's just repetitive, like repeats itself over and over certain symmetry, and it has to stay defined. Because if you have a glass, like volcanic glass, or even glass in your window, if you would look into the atom orientation, there's no such a thing as lattice.
Yeah, okay. So it's about the way they are arranged in the mineral.
Yeah, in the structure, in the lattice. We
Yeah,
call
and
it
it has
lattice.
to be the same for every mineral of that type, and then it's a
Yes.
mineral.
Yes, because you could have, for example, graphite, right? It's carbon. You could also have coal, which is also carbon, but you can also have our diamonds, which is also carbon. But the structure is different, and the structure of atoms defines what it is. And the crystal structure is based on regular internal atomic or ionic arrangements that is often expressed in this geometric form that the crystals take. So if you take quartz or pyrite, which is, the fool's gold, and if you go to mineral fair, it often has this beautiful specimens with this very well-defined crystal structures, right? You have those cubes of fool's gold, you have this nice cubes of fluorite, or you have simple example of quartz, but they have this like columnar with the pyramid on top and whatever.
Yeah, they always look very, very like polished as well, and just
Yeah, they look polished, but they're not polished. This is just how the crystals are formed, right? And this is their symmetry. And generally, the crystals are restricted to 32 point groups, which differ by their symmetry. But the most broad classification is into the 6 crystal families, which are described by the length of the axis. Because if we think about 3D space, right, you have the X, Y, and Z axis. And this is how the crystal grows in those 3 axes, right? Because they are 3D things. And they also have angles in between them. So you kind of describe the symmetry and the crystal forms using those parameters. So the length of those 3 axes and the angles in between each other. And then you have like isometric crystals, which is pyrite. So the fool's gold, the pretty shiny cubes you can buy. Then you have a tetragonal minerals, which is zircon. They're a bit elongated. They have this like triangle on top. Then you have orthorhombic minerals, which is olivine. It's quite interesting mineral, which I'm probably gonna nerd out a lot when we're gonna be talking about formation of Earth. Very cool mineral. Then you have hexagonal, which is quartz, our mineral, which I think a lot of you will know. Then you have monoclinic. Gyps is one of this. You probably know
gypsum.
This mineral. Gypsum.
Mm-hmm.
Yeah. Then you have triclinic, which is anorthite. And this mineral I'm going to be talking a lot when I will be talking about the moon eventually.
I'm still thinking about something you said earlier, which is that's how they grow. Minerals grow. Do they live? How does this work?
When I talk grow, I talk about crystallization. So the crystals crystallize.
Yeah.
But you can also say grow because they can grow in the magma chamber. So when the magma is slowly cooling down, certain elements also will start be enriched enough and bypass the temperature boundary so they can start crystallizing.
Yeah, we can artificially replicate that with ice again, right? In your freezer,
Yes.
when you have something there and all this ice attaches to whatever you have, the ice is also growing in a way.
Yes, although you have to remember that ice often is formed in our fridge because of the shape of the cubes. We have it. But if you think about snow and snowflakes, this is the symmetry of the water, which is freezing.
Yeah, so the shape depends on the kind of mineral that is growing, but the growing system itself depends on the, I think, surrounding.
So this what actually is being crystallized from the environment is crystallizing depends often on what is accessible to crystallize. So I don't know, if you want to crystallize plagioclase, you have to have access to aluminium, silicon, you have to have access to calcium. So
it's like the building blocks of this mineral.
Yes, you cannot create onion soup without onion.
Yeah.
So you have to have those building blocks. Then it also depends on the pressure because, for example, there are different types of quartz which are crystallizing, or like maybe not quartz, the silicon oxide, SiO2, depending on the pressure. So the higher the pressure, the different the structure because it has to be much more compact, right? So the minerals which are created on the surface of the earth have different structure than the ones which are very, very buried deep down because of the
so
pressure.
where they are formed. Yeah.
Yes, exactly. So so the crystallographic family or the structure depends on what is accessible there, the conditions, and also thermodynamics, just broadly speaking. Right? And then the fourth condition to think about something which is a mineral, it has to have fairly well-defined chemical composition. The mineral have a fixed structure, but also can vary in chemical composition. Some minerals have same chemical composition. Generally, you have to know the chemical composition. So like you have to know that if we talk about anorthite, we have to have calcium, we have to have aluminium, we have to have silicon, we have to have oxygen.
It's like the recipe for the mineral.
Recipe for the mineral. Sometimes you have something which we call substitutes. And because of this substitution, like you exchange certain building blocks with each other. Like magnesium and iron are often interexchangeable because they have the same ionic charge. So they are all magnesium 2+, iron 2+. They have similar size, so they can fit into the structure very similarly. And then this is something which we call group. And olivine is one of it. Like I said that olivine is the orthorhombic mineral, right? By the structure. But chemically, it's a mixture of two end members. So you have end member when you only have iron in the structure, and it's called phyllite. And then you have end member which only has magnesium in the structure, and it's called phosphorite. And then you have all this in between series where you, for example, have 60% of phyllite and 40% of phosphorite, but it's still olivine, generally speaking.
So if we take the recipe comparison, you have this new trend of cauliflower rice. It's not rice, but yeah, if you make a dish with this rice, you can have only cauliflower rice. You could have only normal rice or a mixture of the two. Both is still called rice. And it's the same with olivine, right?
Yes, exactly. So you can have solid solution. And it's actually very cool because this tells you, like I said, about the environment this crystallizes. So if you have more iron-rich environment, so you have more iron-rich magma, you will have more phyllite component in it. So you will have, let's say, 80% of normal rice to 20% of cauliflower rice. And then you know that the magma, which was crystallizing from, was very iron-rich. So it was very, very primitive.
Yeah, and you know where to find those things. So you can also correlate that to origin, probably.
Origin. Yes. Yeah, exactly. So these are very important information later on, which we can build on top of as geologists. Because often when I was still in my primary years of geology, I was often asking myself, why do I have to know that? Why do I have to know the chemical composition of all these funny minerals, right? But then it makes sense because the more you know the chemical composition, the more you know of the substitutes, the more you know how other atoms can build up into the structure. It gives you information about where it came from. So like, you know that if it has more of this element of, more uranium, more thorium in it, you know that the rocks or the source of this had to have it in it.
Yeah.
So this is quite interesting, very important for for a lot of people, because like all the trace elements, every geochemist uses this principle that something can be built into a mineral, which is then later on traceable by, chemical composition and analysts. So like we are doing all this instrument work to try to find how much of which atoms we can find in the structure and relate it to the environment where it came from.
Yeah. It's almost like the environment leaves its signature in the rock, literally
Yes.
by replicating the components.
Yeah. We sometimes use a term of fingerprint
Ah, yeah.
because it's literally leaving its fingerprint on the rock by its origin.
Yeah.
And
And we'll talk about how rocks go
formed.
away from their origin,
Yes.
how this process happens. That will be
Yes.
later, but you don't always find rocks at the where they were made,
No.
right?
Often they migrate great distances, and also often they go through various processes. So they can lose content of certain element, they can gain content of element through various processes and stuff like that. It's super interesting. I think this really deserves a separate episode. But it's also quite important to understand that in nature, not everything, or very rarely everything, is pure.
Yeah.
So when we are talking about quartz, we are very rarely dealing with quartz, which is pure SeO2. It often has traces of different elements, like titanium in it. And by traces of titanium, we can talk about temperatures of its crystallization and stuff like this. It's a whole universe of geochemistry, which is fascinating. This is something which I spent a lot of time learning about. I did my master's in geochemistry, so this is fascinating
It's
to
one of
me.
the reasons why quartz can have so many colors, right? Like
Yes,
amethyst is a type of quartz, but it has a very different color than normal quartz.
yes. So amethyst is purple, then you have morion, black, and then you have yellow, which is citrine. And all of it is linked to internal structure or chemical composition of the quartz, right?
Yeah. Yeah.
Yeah.
So it's what
So
we talked about with the structure being the same, but it being polluted in a way with other
yes, it can be
atoms.
polluted by other atoms, or it can be polluted by not being perfect. So
So the structure being
structure
wicked.
being like distorted,
Yeah.
like we have damaged structure, and this can also have physical appearance in the color of the
Yeah.
mineral. Yeah. And then besides the chemical composition and the crystal structure, the description of mineral species usually also includes stuff like habit, which is kind of leading towards how it looks like in nature. Then you have hardness. So how hard is the mineral? This is something which we also describe minerals by. Color, which is quite obvious, right? Then you have something which is called cleavage. And it's not the lady's cleavage, it's the
Oh.
cleavage of the mineral. It's, if you look sometimes at salt, you can see in very big crystals of salt, you can have like fractures, and those fractures often are cleavage. So how it separates from each other, as you would say it. Then you have specific gravity, fluorescence, zoning, and all of this helps to identify and describe minerals. And this is really, really important because right now, as we speak, the International Mineralogical Association, which is the recognized standard body for nomenclature and mineral species, can you guess how many minerals we have described?
Ooh, it should be a multitude of the amount of atoms we have, right? Or elements, I mean. So there are so many
Take a
options.
wild guess.
Yeah, let's say 2000.
Whoa. More.
More. I thought I was betting very high already. Damn. How many?
6,145 mineral species.
Ah, that's a
Yeah,
lot.
that's a lot. That's a lot. And it's quite cool that you can find your own mineral, name your own mineral. You can propose the naming. You can name it after yourself, after your colleague. after the city, which sometimes leads to very funny names like Coming Tonight.
There's a very cool side note I read lately about naming things. I think it was Harrison Ford or one of these very nerdy people in the scientific genre video films and stuff. He was saying to the scientific community, "Stop naming things after me. I'm not a scary critter. I'm just like a guy that loves gardening or something." There was this actor whose name was used for a lot of these very like creepy, crawly kind of animals once they were newly discovered, because we
This
didn't discover many of these insects yet. And he was like, "Stop naming them after me because I'm not scary and crawly."
like generally naming new species, whether it's like flora, fauna, or minerals or fossils, it's so cool and also leads to very funny names
Yeah,
sometimes.
yeah. But people don't always appreciate when you use their name.
One of my former professors from my university in Krakow uh, was actually named Pieczkite. I think that was the mineral. So cool things. I don't think I'm ever gonna be a professor, but if you ever discover a mineral and you lack, inspiration, here I am.
Remember us. Remember this episode.
Remember this episode. And then, of course, let's talk about gems, because my career led me to very specific, very niche job, which right now I'm dealing with gemstones. I'm not a dealer. No, that actually was.
Dealing with
I'm
gemstones.
dealing with gemstones in the sense that I'm doing a chemical analysis of gemstones.
I'm one of those people that thinks in images. I just see you in like one of those dark alleyways, like shining your gems at people,
It's like,
like a
hey,
bat
hey,
signal.
hey, do you wanna go home? I have gemstones in my basement.
In the basement as well.
Yeah. No.
I mean, we would fall for that for sure. They would get us
There's a
instantly.
very narrow, specific community which would probably fall for it.
There's a niche for everything. Like there's always an audience.
Yes. Yeah. It's quite funny how much of transferable skills you can have if you've been geochemist. After PhD, you're like super specialized in one topic, and it's quite hard for you to figure out where your skills can be used. And I was very glad when I heard that this company is looking for a technician to use ICP-MS, which is instrument which can give you very, very detailed chemical composition of your sample to the ppm level, which is below 1% of composition. And of course, like when we talk about minerals, we can add layers of complexity to it. Like I told you, the chemical substitution, but we also can discuss about coordination. You can think about silicon 4 plus, so the ion, and this cation can be bonded to oxygen, right? So it's surrounded by 4 oxygen 2 minus anions. And this is usually oriented in a specific structure in the atomic structure space. It's extremely interesting from scientific point of view because it tells you a lot of information about conditions under which those elements were created, because you can have aluminosilicates like kyanite, andalusital sillimanite. These are 3 different minerals, but they are polymorphs, so they have the same formula of aluminium, silicon, oxygen. But these minerals transition from one from another depending on the pressure. So you can see that if you have certain mineral in the rock, because of how it was formed, you can understand the pressure and temperature conditions of formation of this rock, which lead me to another part, which are rocks, right?
It sounds almost like a villain origin story, that the pressures and the temperatures in the household changes the outcome of the whatever rock in this or
I
mineral in
think
this time.
I often think about it like you're a cop, you're a police, and you have a victim, which is your rock. And you have to figure out what the hell happened based on your tiny, tiny evidences you can have. Chemical composition tells you something, the structure orientation tells you something, and all of it paints a bigger picture of the origin of the mineral, of the origin of the rock. If you know the origin of the rock, you know the more or less tectonic environment it was created in. If you know the tectonic environment, you can understand drifts of continent, you can understand plate tectonics, you can reconstruct plate tectonics. There are people who are like reconstructing position of plate tectonics through geological timescale, just based on that. And there's one more thing I want to talk about. It's the hardness. And I think you know what I'm going to be talking about. It's the Morse scale.
Yes. Very famous, very something you learned very early on in your earth science career.
Okay, so maybe you can tell me what is the Morse scale.
I only know it's a measuring scale of the hardness of minerals. I don't know how it works exactly. I just know we generally scratch rocks against each other, and from that you can see which one is softer than the other.
Yeah, so that's kind of basically it.
And then diamond is the hardest, right?
Yes, it's literally just the resistance for like scratching and indentation of the mineral, and the scale is built in a way that the higher the number, that it it's resistant for scratching for anything below, but it's scratchable by anything which is above.
Yeah. So diamond is at the very top, right? It's 10.
Yes, 10 exactly. Do you know what is the fast one? Do you remember?
Well, I guess gypsum.
Close. The fastest talc.
Fair.
Yeah. Then the second one, so the 2 in the scale of Moss, is gypsum. So how you can translate that gypsum can scratch talc. And then you have calcite as a 3. Then you have fluorite as 4. Apatite as 5. Orthoclase as 6. Quartz is 7. So it's quite resistant mineral.
Oh, I remember this from field work. We used to bring like these pocket knives, and if it scratched the pocket knife, it was quartz, I guess.
In the rock.
Yeah.
That's, or like, it could be, quartz or anything above quartz, right?
Yeah, obviously.
Yeah.
But you don't find diamonds generally in Spain, somewhere high in the mountains.
You could find like tiny corundums, it happens. But generally, the rule of thumb, I also had this, like we were scratching our geological hammers, and then like if it was scratchable, then it usually means that there's indication of having quartz in the rock. Then you have above quartz, you have topaz, then you have corundum, and then you have diamond. So this is something which is, often used to indicate the hardness of the mineral. So if you see description of like certain mineral, and then you have hardness, and you have hardness of like 8.5. So you know that you can scratch topaz with it, but you cannot scratch corundum with it. So, but talking about rocks, I'm not going to be talking a lot about it because I want to kind of make it separate episodes based on the distinct different types of rocks. But generally, like I said, the rocks are made of minerals. Sometimes also like amorphic matter, like obsidian, but mostly rocks are made of minerals. And it has to be again created by a specific geological or cosmological process. So again, when I was working during my PhD on piston cylinder, so I was creating my own artificial rock samples. These were not rocks nor minerals. So these were samples, specimens. And the rock can be consolidated or non-consolidated, which means that it can be hard and like sticking together, like normal rock when you think about it, or it can be non-consolidated.
Yes,
also
it's either compacted and sticks together or loose.
Or not. Yes, or loose, exactly. Then you have monomineral or polymineral, which means that it's only made of one specific mineral. For example, you have quartz, and then you have a quartzite. So it's rock made of quartz.
Yeah. So do they have to be separate, like grains of quartz sticking together?
Yes, they are usually, if you talk about quartzite, it's just metamorphed quartz together, smoothed.
So compacted.
Then you have sandstone, which you have sand, and you have a matrix when those sand grains are enclosed in cement of some sort. It can be like quartz, like it can be, I don't know, calcite, like, and then the calcite is in between the grains and it just sticks it together as a cement. And then you have a polymineral, which is something like you think about granite, and granite has quartz. It has also other minerals like muscovite and stuff like that. So not only one specific mineral, but few minerals together. One disclaimer: soils are not rocks. It's quite important to remember. Soils are not rocks.
No, because they're loose, right?
Yes. And then from the genetic point of view, there's this division proposed by German geologist von Kott in 1862. Remember, in 1862, the German was prevailing scientific language for geologists.
They were still hip and happening.
They're still hyped for another 50 years, and then the First World War happened. So he divided the rocks of the Earth crust into 3 different categories: magmatic, sedimentary, and metamorphic. And these magmatic and metamorphic rocks are often called crystalline because they are composed of crystals. As simple as that. And then in case of earth science disciplines which deals with these rocks, it's called petrography. And petrography often describes the rock in case of texture, structure, composition, color, all these things. Texture and structure tells you about how the minerals are oriented towards each other. So it kind of describes the rock for you, using very specific scientific jargon, because it deals with the size of the grains and stuff like that. For the first year of geology, if you're doing rock geology, you will be just doing that. You will be just describing rocks.
Because you can only understand it if you describe it like many times, apparently.
Yeah, you start linking certain textures and structures to geology, like geological orientation. Like you're gonna see that this specific type of rock is prevailing in this specific structure, and then you can start making, different connotations. But first you have to just learn how to correctly describe it, because other people also have to read it, and other people also have to understand, to visualize what you've been told, which leads to, again, discussion with scientific language, why we develop such a specific jargon, such a specific terminology. It's because we have to explain what we see in the field to other people so they can believe us that we actually saw it, and it actually, in a convincing way, that they actually, whatever we conclude based on our observation, makes sense.
Yeah, it's like learning to speak the language of rocks.
Yes, that's so poetic. I speak the language of the rocks. And then you have petrology, which sounds quite similar to petrography, but it also adds another layer to it, which is the origin, where this rock came from. And this links with geochemistry, which tells you about geochemical composition of the rock. So it tells you about chemistry. And then you have sedimentology, which deals with sedimentary rocks. And then it also uses petrography because it still describes it, and often also uses paleontology because in the sedimentary rocks, you often find fossils, right?
Yeah.
So this is something which you're going to be talking about soon in the next episode.
Yes, I know very little about the metamorphic rocks and magmatic, I don't even know the right
magmatic rocks.
terms.
Yeah.
Whatever. But I know more about the sedimentary rocks, and I find it fascinating how you can look at a wall of sedimentary rocks, all different kinds, all different layers, and tell a story from just looking at this wall of rocks.
It's like a book.
Yeah. And if you know how to read it, if you know the language, again, you know how to read it. Yeah. Yeah,
I love it.
That still marvels me every time.
So that would be it. So next time when someone asks you, what is this nice mineral? You can just be like, oh, I can tell you that it's definitely a rock because it has a lot of minerals in it. And then if someone shows you quartz, you can be like, hey, you know that purple version of quartz is called amethyst. And then there's a black version of quartz, which is Morion. And all of that is SeO2. But it's not so often pure SeO2. It can have titanium in it, which tells you about temperature and pressure, because everything leaves trace.
That's where we're going to end this episode. See you next time.
See you next week.